So let's revisit some more concepts before we move on. Oops, okay, sorry. Here we are. We had looked at this in the last chapter where we had derived the geostrophic shear in the pressure coordinate for the atmosphere, which looked like this. It's called thermal winds, basically because it's dependent on temperature gradients in the meridional and zonal directions. Right? Obviously, to remind ourselves, we had moved to pressure coordinates to get rid of density and use ideal gas law to move into temperatures. And we argued that remembering our thermal gradients in the meridional direction, zonal mean meridional section, not only was temperature decreasing from the tropics to higher latitudes, the gradient of the decrease was increasing with altitude. As you went up from near the surface to upper atmosphere, the drop in temperature was steeper and steeper. So the tropical tropopause is higher, 12 to 15 kilometers, and the tropopause drops off to about 8 kilometers as you go into higher mid-latitudes and higher latitudes. Using our thermal wind balance, we said geostrophy has to be modified to create these geostrophic shears, which gave us this vertical structure of zero winds at the surface because of friction and strong winds in the upper atmosphere, the jet streams, right? The details we will add here is that the Hadley cell, which you have been happily showing as a zonal mean meridional cell, it turns out that the strongest zonal winds do not happen where the Hadley cell terminates. They happen much further poleward. Okay, we have to understand why that is. And the little secret, actually we don't exactly know why Hadley cell terminates where it does. Is it because of the beginning of the baroclinic instability, or is it because of some balance between the energy being transported by the Hadley cell and the radiative losses that we talk about in the subtropical highs? Remember, we said air is coming down, subsiding in the subtropical highs, it's compressing and warming, but the buoyancy doesn't go up because there is also a radiative loss. So there is a balance between the two, and the air sinks pretty slowly. Okay. So Hadley, on the other hand, had said trade winds in the equator, in the deep tropics, are explained by the Earth's rotation and the effects on the winds. And he said at high latitudes the winds are westerly all the way from the surface to the upper atmosphere, and the deep tropical easterlies become westerlies in the upper atmosphere. So he imagined that there is a circulation in the upper atmosphere going poleward, except he assumed that it would go all the way to the poles. Right? He still wasn't aware of angular momentum conservation, baroclinic instability, complete effects of Coriolis, and so on. And he had winds converging into the low latitudes all the way from the poles to the low latitudes. We already know that that is not exactly true. We did this analog in the lab experiment. We rotated the water tank and we released water at the edges with omega R1, the rotation of the tank, and the water parcels do not exactly follow the speed of the water tank unless it's in a solid body rotation. Right? In a solid body rotation, this entire system is moving together. So if you set up a solid body rotation and reduce the rotation speed slightly, then the inertia of the water continues to move, and it creates motion relative to the tank. So you get relative azimuthal velocities, which is dependent on the distance from the outer edge where you introduce the angular momentum. So omega R1 times r1 is the angular momentum, v theta r is the angular momentum of the water parcel at r from the center. So we said the azimuthal velocity is amplified by this r, the distance from the center away from the wall. Why is it important? Because same thing will happen. The Earth is delivering angular momentum to the air at low latitudes through friction. That angular momentum is being transported poleward, and it's getting amplified by r because the local r from the Earth's axis to the location at any latitude is reducing as you go from the equator to the pole. So the v theta, in our case that would be longitudinal flow, or the zonal flow as we call it, will be amplified. See how the ideas connect. That's what you need to be able to do. Understand the physics enough to move from the tank to the sphere and translate these from 2 dimensions to 3 dimensions. Okay, fairly straightforward stuff. So we need to understand the mechanism behind these circulations. These are overturning stream functions, annual mean, seasonal cycles for the boreal winter and boreal summer. I hope we are all familiar with boreal and austral by now. Boreal is northern hemisphere, austral is southern hemisphere. Boreal winter is December, January, February. Boreal summer is June, July, August. We said the sun moves, the heating moves, rising motion moves, Hadley cell moves. We'll see an animation to reaffirm this concept, even though we have said it already many times. So you can see clearly a stronger Hadley cell here in the winter in the northern hemisphere than here, because the ITCZ has shifted with the sun to the south, so the northeasterly trades get stronger and so on. Whereas in JJA you can see that it's stronger more towards the southern hemisphere. Obviously there's cross equatorial flow. Okay, we'll see that producing cross equatorial flows is much more difficult in the ocean, because crossing the equator means you're crossing the sign of the Coriolis. Remember, it's negative in the southern hemisphere, positive in the northern hemisphere. So you need friction to change vorticity, or the rotational tendency of the fluid. In the atmosphere it's easier because it moves fast and there is friction at the surface. Okay. So, simplifying by ignoring seasonal cycle and the diurnal variations. I already mentioned seasonal cycle here, but most of the energy arguments we will make for the general circulation will ignore the seasonal cycle, which obviously is important, but it just modulates the general circulation by doing this. So, Hadley cells are always there, but they are modulated by the seasonal cycle. Okay, so it's easier to ignore it. Diurnal variations are important, but for example, as the sun rotates from west to east, there are night places where it's night, and there are places where it's day. So it should have a strong thermal gradient, but the inertia of the atmosphere basically smooths things out, and the diurnal cycle for the general circulation can be ignored. Okay. Where will we go with it? Obviously we'll go back to our energy balance in the annual mean. Meridional energy transports in the annual mean. So this is what gave us the seasonal cycle, as you remember, the tilt and rotation around the sun. So you had the seasonal cycle, but because of the tilt, summer pole faces the sun, winter pole faces away from the sun. So seasons move. Okay, all the basic stuff, but I'm just repeating it in the context of where we are headed, so that you don't forget, that you remember all the concepts we've been building up to now. It's good to repeat them. It's good to look at the figures again. Figures are critical in my mind, because if you can look at the figure and explain the physics, then you have understood it well. You don't need the equations in that case always. You can find the equations in the book, but figures, even if they are in the book, you should be just able to look at them and explain the physics. If you are able to do that, you are good.